such series is that summation n equal to 0 to infinity n times x power n is x over 1 minus x whole square. You use this formula to solve the above summation. So x here is lambda by mu. This term can come outside the summation, and this is summation n times x to the power n, where x is lambda by mu. What is this? Anyone? Any questions, comments? Is there anything that is not clear here?
What you got? Lambda over mu over 1 minus lambda over mu.
Yes, if you bring that lambda inside, so this is exactly right. So this will become lambda upon mu minus that. So your expression is right. So just multiply the lambda in the denominator.
Can you explain that a little further?
Sure. So you basically take 1 minus lambda by mu outside. Inside is summation n times x to the power n, which is x over 1 minus x whole square. So this second power cancels with this because it is the same. Then I multiply with mu in the numerator and denominator. This is lambda over mu minus lambda. We already did that for stability of the system, lambda has to be less. Otherwise, the number of customers in the system will blow up to infinite. Does that help? Any questions on this? Anyone? Any questions here? I assume that this is very clear. All right, let's continue then. Okay. So there was a question last time. Can we also give expression for MMS system? We can use the formulas. So rather than going into the analysis, I'm directly giving the formula. And you can use the previous expression and substitute and try at home. Um, but we won't be asking this. So I'm just doing this because there was a question last time. So if it is MMM system, then pi 0 is 1 over 1 plus summation n equal to s lambda by b n summation n equal to s plus 1 infinity lambda by s the n s to the s over s. That's how pi 0 turns up as by doing all that summation, and pi n will be 0 lambda by mu n over n factorial for n is equal to s and pi 0 times lambda by s mu over n s to the power s factorial n larger than s. So this will be the expression when you solve for a general MMS system, using our formulas for general birth and death process. So you don't need to write down these expressions or remember them. These are just given for completeness. That the expression that the formula we give for general birth and death process is valid for other cases too. Just that for MMS, the expressions get a bit messy, but can still be derived from there. Okay, let's continue further. So we are pretty much done with birth and death processes. Now we'll take a step further into the next chapter. The next chapter that we will work towards is queuing theory. Some of the previous examples that you saw, like the MM1Q, MMSQ, and all those, we were already doing kind of queues as a special case of continuous time Markov chain. So this means queuing theory is essentially a special case of continuous time Markov chain. So you basically have arrival process, a departure process. You have a bunch of servers in the system, and you have a queue where you're waiting. So think of a Starbucks type system, which is a good example to think of. that you have customers entering the system, you have certain number of servers, each with a service time, and then they leave the system after being served. So in this type of system, we care about a few metrics. So some of the metrics that we care about are L, which is called the average number of customers in the system. Is it clear what does in the system mean? In the system means whether they are in the queue or at the server being served. So combining all of them. So the number of customers that are in the queue or being served. Is that clear? The second expression is LQ, which is called average number of customers waiting in the queue. So LQ does not include the people that are with the servers that are being served. It's only counting the people that are waiting in the queue. Next expression W. The W is average amount of time customer spends in the system. This means from the time you enter the queue to the time you depart from the server. So after getting served, so the total amount of time you are in the queue as well as with the server. Does that make sense? The definition of W?
Could you repeat that definition one more time, please?
Sure. So this is the average amount of time customer is in the system. In the system means whether you are waiting in the queue or with the server, combining everything from the time you enter to the time you receive the service.
That makes sense. Thank you.
So the next definition is
Does in the queue mean that they're they're waiting or they haven't been born yet? I guess is maybe the term.
they so like you are going into a Starbucks or um, any shop, so you are first in the queue before you enter the server to order your stuff, right?
Yes.
So in the system, in the queue means before you reach the server is in the queue. You are waiting in a line. Then you basically go to the server, and that is basically the service time, the time you spend with the server. So W,
And then that's out of the system.
yeah, after getting served, you are out of the system. So yeah, means you can think of any type of queue, even like an airport queue. You basically are doing the you're entering the system for getting your ID checked, and you basically enter a queue, and then there could be multiple servers in front of you. The time you are waiting before the person sees your ID is the time in the queue, and then the time the person you are with the person for your ID check is basically the service time.
Okay, that makes sense. Thank you.
So WQ is the average of time customer is waiting in the queue. This is basically before the person gets starts receiving service. The time the person is just in the queue waiting for service. Is that clear? So for different types of queuing systems, we would have to calculate these four metrics. So let's see what formulas could help us in computing these type of metrics. In order to compute the formulas between them, let us define another notion, which is called lambda A, which is defined as average rate of entering customers. So, which essentially means that if NT customers enter by time t, by t, limit t going to infinity is lambda A. So, which means how fast are the customers entering the system? Now, for MM1 type of system, customers were always entering at the rate of lambda. So, lambda A was lambda. In general, the incoming rate could depend upon the number of people in the system. So, take for example, saying that we might not, we have a limited capacity. After a certain point, we basically say, you have no service, please return back. So, the arrival rate of the people entering the queue may be different from the actual of the customers. So, lambda A is the average rate for the customers that enter the queue. Okay. We will do more examples, but to explain what lambda A is and why it may be different from lambda in certain cases. But lambda A essentially is the rate of customers that enter the system. Is that clear? Is the definition clear? Great. All right. So given that we have defined lambda A, which is the average rate of entering customers, there is a result which is called Little's formula, that says L is lambda A times W. So this relates the notion of L to the notion of W by the arrival rate. Further, we have LQ is also lambda A W. Assuming homogeneous customers. Uh, so essentially, what Little formula does is it relates L and W and LQ and WQ using the arrival rate. Any questions here before we do an example for MM1Q? We'll write down all the expressions for MM1Q just to make it. Is the latest formula clear?
To clarify with the lambda A, you're using that because sometimes throughout the system, depending on how many customers you have, the rates could, in theory, be different.
Yes. So depending on number of people in the system, the arrival rates could be different based on the definition of the queuing system.
Okay, gotcha.
So people may do some admission control into the queue, right? They may say, "Oh, the queue is getting full. Please don't enter this queue. Go somewhere else." Something like that, right? So your this is going very general, so that's why any type of queuing discipline is fine. So there may be any form of admission control or anything that is controlling how many what is the rate at which the customers can really enter the system. So if you remember, even in birth and death processes, which is kind of a queuing system, we can set it up as a queuing system for a certain arrival rate and departure rate based on the number of customers in the system. We did not have a lambda. We had a lambda n. We had a lambda which depended on the number of customers in the system. Right? So in general, the arrival rate could be controlled by any process. So this is basically the number of customers that can enter the system based on your problem. Is that fine?
Yeah, that makes sense. Thank you for explaining.
Sure. And we'll do more examples. I think it will get more clear when is lambda A, what is lambda A in different examples. All right. So we'll start with the simplest example first. The first example we'll do for all these metrics is the MM1. Right. Earlier in the lecture, we computed a metric which was average number of customers in the system for MM1. We computed that as lambda upon mu minus lambda. Right? Which of the LW, LQ, WQ is this number? Can you relate it to any of them?
The L.
It's L, yes. So we already computed L here, which was lambda upon mu minus lambda. So in MM1Q, we already computed L as lambda upon mu minus lambda. Okay. In this case, the customers keep on entering at the rate of lambda. So our lambda A is actually lambda, which is the average number of arrivals in the system. All right. So with that, what is W? Just little slow.
Is it um 1 over mu minus lambda?
Yes, exactly right. So this is L over lambda A, which is L over lambda, which is 1 over mu minus. All right, I have computed W. What is W? W is the total amount of time in the system, which means in the queue and getting served. So I have to compute WQ, which is the time in the queue. How would I calculate that from the previous expression? So I'm given the total amount of time in the system. I want to figure out the time in the queue.
It's the W minus mu.
W minus, you are very close. W minus what? Mu is the rate, not the time. It is exactly W minus expected value of service time, because the total time includes the service time and the queue time. So you only have to reduce the service time. And W is 1 over mu minus lambda. It is expected value of service time. So you go to a customer, what was the service time for MM1? The definition of MM1 was that customers are entering into the system with the average arrival rate of lambda, and there is a single server who is serving at the rate of mu. Okay. If there is a server that is serving at a rate of mu, what is the average amount of time person spends with the server?
1 over mu.
Yes, 1 over mu.
Can I ask why? When did we set the lambda A equals lambda? Was that just an assumption? Or why did
No,
we
that's not an assumption. That was by definition of MM1 queuing discipline. So in MM1 queuing discipline, the people keep on entering at a rate of lambda. So the average arrival rate becomes lambda.
You just
We see number of customers that enter into the system is a Poisson process here with the rate of lambda. And the definition of lambda A is the average arrival rate of that process of entering customers. So since MM1 said that the arrival rate is a Poisson process at the rate of lambda, lambda A becomes lambda.
So we're not like limiting the entrance of customers at all, just like anyone who arrives can come in right away.
Yes, yes. In MM1, we are not limiting anybody.
This also is due to the memoryless property, right?
It's because of memoryless property, and of course, the queue at certain time may go very, very large, which can happen because of the stochastic process. So we are not limiting anything in MM1. Yeah, but the rebel process is the Poisson process, which is why rebel rate becomes just lambda. So we can simplify this, take the LCM, and you will get lambda upon mu times mu minus. Any questions so far? Right, last metric. What is LQ?
Is it just WQ multiplied by lambda?
Yes, by Newton's law. Lambda times WQ, which is lambda squared upon mu times mu minus. All right. So you see, it was not very hard to compute all these metrics, at least for MM. Let's just try to interpret these formulas. Suppose customers at Amazon rate of on every 12 minutes. Service ID is exponential at the rate of exponential at a one service per 8 minutes. What is L and W? So what is lambda?
Minutes.
1 over 12. Yes, it's the rate. So it's the inverse of time. What is mu?
Length.
1/8. Then L was lambda upon mu minus lambda. So what is L? Lambda
Negative
upon
2.
cannot be negative 2. Mu is larger than lambda.
What is the formula?
Lambda upon mu minus lambda.
Just 2.
Yes. And W is, so note that none of these expressions can be negative. If they're negative, that means the Q is unstable. Something is wrong. So what is W?
1/6.
You, I think, multiplied or divided the wrong way. W will be L divided by lambda. So 2 divided by 1/12, which means 2 times 12. Okay. L value, which is 20. Is it clear? So then the next question says, suppose arrival rate increases by 10% to become, 20% to become 1 per 10 minutes. It used to take 12 minutes. If I'm 20%, if people are coming 20% faster, then it becomes 1 per 10 minutes. So if it becomes 20% faster, the new lambda is 1 by 10. Then what is L and what is W? So same approach, just change lambda from 1/12 to 1/10. What is L? Lambda upon mu minus lambda. Lambda is 1/10, mu is 1/8.
Four.
Okay. And what is W?
W is 40.
Yes. So what you see is I only increase the arrival rate by 20% and the number of customers in the system doubled. So I slightly increased, means 20% is not that big of an increase. So I only increased 20% of the rate of people entering the system, and my length of the, means the number of people in the system, are close to doubling. Can we explain why?
It's dependent on the service time, right? Because if your service time can't get through the new influx of customers, then it's just gonna bog
Right.
down the system.
Yeah, it's still lower than the service rate. So, but yes, the intuition is correct. So what is happening here is L can be written as lambda upon mu over 1 minus lambda upon. So 1 over 1 minus x, basically when lambda over mu gets closer and closer to 1, this basically goes up like very large. So if I have to plot lambda over mu here, and of course we cannot cross lambda over mu as 1, the L will grow like this. So as lambda over mu keeps on going to 1, this basically goes exponentially up. It goes very fast up. So if you basically increase even a slight bit, the L increases very fast. Does that make sense? So similarly, W will also increase very fast because W will be 1 over mu upon 1 minus lambda upon. So as lambda over mu approaches 1, the increase is significant. So when you are closer to the service rate, the queue length, average queue length, average people in the system increases very fast. The same is true for LQ and WQ too. We just did not write those expressions, but if you write down those formulas, they pretty much have the same type of relations. So people in the queue or people in the system will increase very fast when lambda over mu approaches 1. So
If your arrival rate is greater than your service rate, then you'll always basically have
then
infinite
none of the
people in the
expressions
queue over
hold.
time.
No, then none of the expressions hold. If the arrival rate is larger, then your system is unstable. You can't have a finite queue.
Oh, I see.
So then none of the pi equations are valid. The system is not ergodic. Nothing is valid. So every expression will work if the system is stable. So if there are more customers entering and people cannot leave enough, then the queue will immediately build up to infinite. Does that make sense? So, since there was also a question of what is lambda A, let us take an example of birth and death process and just parse it. So, in birth and death process, in general, lambda A is nothing but summation lambda n p n, pi n. So, if lambda depends upon the incoming rate depends upon the number of customers in the system, then lambda A also depends upon number of customers in the system. So the different arrival rates when there are n people in the system. So that's how it will happen for birth and death process. Okay. So let us do another example. This was just an intuition of how it would happen in general for birth and death. Let's do a simpler example, which is I take a MM1 type of system, but with the change with finite capacity. With finite capacity, what I basically say is if there are n customers in the system, I will not let anybody enter the system. So no customer enters if n in the system. So you have a finite capacity. Think of going to a Starbucks and their queue their system can only incorporate, let us say, 100 people waiting in the line. After that, due to regulations of the building, nobody else can be there. So they basically say, do not wait, just move out. Okay. So they cannot enter the queue after a certain number of people. Does this make sense? No problem. So in this case, we can set up the. This is also a birth and death process. So we could use the birth and death process equations, or we could basically set up the system of equations like before. So we have state, rate leaving. So let us basically make the states just for simplicity. State is again number of people in the system. Okay. So you have 0 people, 1 people, n minus 1, and n. Every state you have arrival rate of lambda. Yes, that at n you don't have any error. Right? So once you are at reached n, then there can be no other errors. And then their departure is the setup clear? So it's birth and death system where lambdas beyond this are 0. Right. So we can write down the system of equations. Rate leaving state opening or 0 state. What is the rate of leaving? Lambda times pi c. Rate of entering is mu times pi. Any state from 1 to n minus 1. The rate of leaving is lambda plus mu pi n, and rate of entering is lambda from the previous state and mu from the next state. So far, we basically wrote the same equations as in MM1 system, just that capital N was infinite there. And then for capital N, we have mu. You only enter if there's a departure equals lambda pi n minus 1. Sorry, these are all capital N's here. This equation is clear? So you can solve it the same way as we did before. So lambda pi 0 will come in the first equation. You cancel certain things and make those equations. And you can solve similar to what we did on a birth and death process. So once you solve those, you'll get pi 0 is 1 minus lambda by mu over. So in the MM1 case, we only had 1 minus lambda by mu. In this case, we have 1 minus lambda by mu upon 1 minus lambda by mu power n plus 1. So note that if n goes to infinity, then the numerator becomes 1, which is where we get the MM1 result. So pi 0 is this, and similarly, pi n becomes lambda over mu n 1 minus lambda upon mu upon 1 minus lambda upon mu just Can you still see whiteboard or not? You can. Okay, I cannot. Oh,
You can drag it to move the view. It's like you can zoom out and zoom back in.
okay, found it. So, okay, lambda by mu n 1 minus lambda by mu upon 1 minus lambda by okay, I might go to the next page. Maybe at the bottom it's calculation. So pi n is lambda upon mu n 1 minus lambda by mu upon 1 minus lambda by mu power capital N plus 1. So it's basically the same expression for every pi 0 and pi n. Of course, n is only from 0, 1 all the way to capital N. After that, it is 0. So only thing that changed is the normalization. We added a denominator because pi n was 0 after n equal to capital N. Okay. The numerator was what we had for MM1 system. The denominator is what got added because of the finite capacity.
From the perspective, just out of curiosity, from the perspective of computer simulation modeling, would the computer use the matrix method or would it use these formulas to calculate this?
If you have the formulas, I think formulas are always faster and more accurate. Because think of it this way, these are powers, right? So numerical precision always comes into the picture if you solve bigger matrices.
Even with like some of the ones earlier that were like factorial.
Yes. So yeah, and these are solving them, right? You won't have to worry about them. These are just directly computing almost. In general, you have a matrix of matrices doing the inverse. You have much more numerical precision than the formulas, right?
Mhm.
So matrix inverse, think of the error that will be order of n square, which is where n is the number of entries in the matrix. So here you won't have that scaling of the errors.
Right. It gets rid of the errors because when yeah, I remember learning about that. Okay. Gotcha.
Yeah, it's basically the error propagation, which is why we always prefer closed form formulas. Otherwise, yes, matrices would work. But then other thing to note is there are no matrix formulas because these are infinite by infinite. Because of finite capacity, we were able to get it n by n, right? N plus 1 by n plus 1. If n was infinite, then these are infinite sizes, which is why we had to use the equations. There are no matrix forms for infinite by infinite, right?
Right. That would be a feasible way to compute that.
Yes, and that's why for birth and death processes, we actually computed them closed form rather than relying on matrix inverses because there's no matrix. So then you basically have computed all the pi n's. L is summation n times pi n for n going from 0 to capital N. So I could again take 1 minus lambda by mu divided by the denominator 1 minus lambda by mu n plus 1 summation n equal to 0 to n times lambda by mu to the power n. Now you see n times x to the power n. You could use the same approach with the caveat that this is only a finite summation, not an infinite summation. Okay. So you can solve the AG series using the approach you used before, in your previous courses or high school. I'm directly giving you an expression by solving this AG series. So once you solve that summation, L will be lambda times 1 plus n lambda by mu n plus 1 minus n plus 1 lambda by mu n by mu minus lambda 1 plus n plus 1. So that's how the new expression comes.
Can you go back to this page really quickly? I just missed. Yeah.
That would be page 10.
Thank you.
Are we multiplying the last summation that is underlined by what's next to it?
N times this, yes.
Okay.
It is summation of n times pi n, right?
hmm
Are you multiplying like the thing, like that whole last row is one big equation? Or like one big thing you're multiplying all together?
This is just one big expression, lambda times we have the square brackets. So you have to compute the thing inside the square bracket, which is 1 plus something minus something.
No, sorry, on the previous page that you were on.
Okay, which expression are you
Like-
talking about?
Like the whole last row after the equal sign, like you're multiplying that all together. The fraction on the left is the
Yeah,
summation.
this divided by this times this.
Okay.
What I did here was I took this numerator and denominator outside the summation, nothing else, because those were independent of small n. Right. Now we have L. In order to compute W, we need lambda A. So what is lambda A here? So you have a birth and death process. I already told you that it is lambda summation lambda and Pn. So slide 8 is where you basically saw this birth and death process. So what is lambda A? What is the arrival rate in state 0? What's the arrival rate in state 0?
Just lambda.
Yes, in state 1. State 1 in lambda. State n minus 1. Where's the arrival rate in state n minus 1?
How is the arrival rate to state 0 lambda?
From state 0, the arrival rate is basically when a new customer arrives, and that is at the rate lambda here. So if you remember
it's
the
like leaving
birth and
state
death,
0.
yes. So in birth and death processes, this was lambda 0, lambda 1, lambda 2, lambda 3, and so on, right? Those were the arrival rates. So lambda n's were, this was lambda 0, lambda 2, and so on. So what was lambda n? What is lambda n minus 1? Where's the arrival rate at n minus 1?
Still lambda.
Still lambda. What is lambda at capital N?
0.
0. And that is basically what changes the picture, which is lambda A is lambda pi 0 plus lambda pi 1 plus all the way up to lambda pi n minus 1, but 0 at pi n. Which is lambda times pi 0 plus all the way up to pi n minus 1. Now the sum of all the probabilities of the states from 0 to n is 1. So this is also lambda times 1 minus pi. Is that clear? So the basic thing is when there are n customers in the system, you are not having arrivals, which is why your actual arrival rate reduces because at the state n there are no customers, no customers entering the system. So average number of customers enter the system is only when You are not in the state n. So your actual arrival rate reduces by 1 minus pi n. Does this make sense? So we already computed L. W is L over lambda A. And lambda A was 1 minus pi n. We already gave you the formula for pi n. Okay, so pi n formula.
Just to clarify,
Mhm.
basically, intuitively, what's happening is that even though the customers are always entering the states at a constant rate of lambda, because there's a limiting amount of states or amount of customers that you can have within your system over a long period of time, that would basically mean that the rate is decreasing.
Yes. Yes, because you are not having the customers enter when you were in the limiting state.
Gotcha. Okay. And if you have like a really large queuing size, like total amount of people that you can have in your queue,
Then you won't have
much, then you don't have this issue. Okay, gotcha.
that
That
was
makes
the
sense.
MM1 system, right? Because in MM1 system, n was infinite.
Right.
So when capital N is infinite, all these expressions will boil down to MM1 system. So, okay. So we now know what is L. We give you the expression. Lambda A is lambda times 1 minus pi n. Pi n, we give you the expression. So that could be computed. Now, what is WQ? What is WQ?
It's W minus expected service time.
Yes, W minus expected service time, which is 1 by mu. It's the same. Okay. And similarly, LQ is lambda A WQ. So LQ is average number of customers in the queue. Alright. So you can use this to calculate whichever expression you want this system. Any questions for this?
So kind of in a real world scenario, I'm assuming you have to pick your big N, right? So would you
Yeah.
just kind of pick that as like, I don't know, if you're Starbucks, that's the capacity of your building, like to be really on the safe side of that?
Yeah, so you basically could define your profit based on number of customers that you can have and the cost it would take to build the facility with that much queue. And you can basically make all these hyperparameters to optimize.
Gotcha. Okay. Yeah, so there's an optimization problem within that.
Yeah,
Wow.
but we are basically doing the metrics. Once you have the metrics, you can set up a facility planning problem.
Oh. Oh yeah, that's interesting.
So we'll go over one more facility planning way you can basically model the system, and of which this will be a special case, and that might be more realistic in the system. So let us go another example, another formulation. So we did MM1 system. We did MM1 system directly. We did one with finite capacity. So there is another modeling that people do typically for MM1 system, and they call it with bulking. How do you pronounce this word? Balking. Would you pronounce BALK?
Lol.
Okay. So
Bulking.
what this sure. So with bulking, what they do is, um, if n in the system, customer joins with probability alpha n. So intuitively, what is happening is you go into a Starbucks, you see a lot of people in the queue, you will like, let me go to another store, right? Let me go to Grey House. So if there are a lot of people in the system, the customers will already kind of start leaving the system. Does that make sense? So if they are in the system, customer will not join the system. Customer will join the system only with probability alpha n. In this case, lambda n will be lambda times alpha n, because with alpha n probability is only when the customers can join the system, otherwise customers will not join the system, and mu n will always be mu. So this is more generalized than finite capacity. So MM1 with finite capacity is a special case where alpha n is 1 if n is less than n, and 0 if n is larger than equal to n. So in MM1 finite capacity, we said you would always enter the system if there are less than n customers. You will never enter the system if there are greater than or equal to n customers. But in MM1 with bulking, you can have the customers enter the system at the rate of alpha n when there are n people in the system. So this is just a generalized form of finite capacity, and the approach is pretty much similar. Okay. So we are not solving MM1 with bulking. That would make the expressions a lot more messy. But at least that gives you an exposure that if you can do if you're doing a facility design type of problem, and you can get a survey of what alpha n will be like and what finite capacity you might have, then you can design the system that way.
With this assumption, or I guess state, does capital N go from the capacity to like the point at which customers start looking for other options?
Yes, so it might be that way. You can also impose another condition when you cannot even have the people enter. So it's both ways, right? So there is a human tendency of not joining bigger queues and looking for other options, as well as people, and as well as basically compelling people not to join if you are greater than a certain number because there's a capacity of the building. So both those factors could be factored in this MM1 with barking type of systems.
Like a real world example where this like might happen. Let's say you have some sort of amusement park or movie theater or something like that, where there's like one way to serve the customer, and then as soon as like over time, probably as there's so many people in the queue, people are going to stop wanting to go on that amusement park ride because the wait is so long.
Yes. Yes, that is one good example. Other good example, as I mentioned, was you have Starbucks and Grey House close by to each other. Then you may want to basically leave Starbucks to Grey House if there are more people here.
Sure. Okay.
So yeah, means people may like one type of coffee better than the other, but then of course there's a trade-off of the time.
So it's like a demand elasticity.
Yes. Yeah, it's kind of that. So that's how we basically model the system. But once you have modeled the system, you can analyze the system using the approaches that we did in this course. And then you have the metrics, and then you can put that into a big optimization problem of your planning and designs and everything that you need. Does it make sense as a practical way how you would use this type of things that we learned? So I think we are at time. So if there, let me know if there are any questions for the remaining 3 minutes, and I think we are done for today.
Thank you. Have a good day.
Thanks.